Hello, I'm Patrick Smith, a junior aerospace engineering major at the University of Alabama in Huntsville, who studied with Dr. Kanistras this past summer through the RCEU program on campus for the use of polyvinylidene fluoride films as sensors for pressure measurements. To begin, a discussion of aerodynamic pressures is necessary as we looked specifically at the application of PVdF films for aerodynamic purposes. Aerodynamic pressure comes from whenever air flows around a surface, it gets squeezed by the surface and it squeezes the surface, changing its pressure as the flow travels. This distribution of pressures in the flow itself actually accounts for a large amount of the aerodynamic forces present within the flow. The pressure actually gives insight to the state of the flow as well, whether or not the flow is attached to its surface or if it's turbulent or not. As is, pressure taps are typically the main way to gather information about aerodynamic pressure in a flow. However, these practices, pressure taps, can be invasive to the flow and expensive to implement. Moving on to piezoelectric materials, this topic is necessary in order to understand polyvinylidene fluoride, as polyvinylidene fluoride, or PVdF, is a piezoelectric material. Piezoelectric materials naturally generate electrical charges whenever they are deformed in some manner. Due to this deformation, they are natural pressure sensors, as a pressure acting on any material can cause a mechanical strain on the material itself. This strain is what then leads to the electrical charge, and in a way, these are completely passive pressure sensors, which makes them unique in a field where most pressure sensors are active. Their electrical signals decay, however, with time due to the fact of natural irregularities and imperfections in the material itself, and they need to be amplified through a charge amplifier in order to convert the signal from a flow of charges into a voltage difference and also to magnify this difference. You can actually see a charge amplification circuit on the right, which is from our friends in Purdue. Additionally, polyvinylidene, just to specify what it is a piezoelectric film, but it has a lower sensitivity than some of the other piezoelectrics out there, such as the ceramic piezoelectric. Dr. Kanistras and I were specifically interested in the use of these PVdF sensors for aerospace applications. In order to verify that these sensors could be used for aerospace applications, we had to verify that they could be used in the aerodynamic pressure ranges. These aerodynamic pressure ranges are much smaller than the mechanical pressure ranges that these sensors are commonly used for. In order to test the material to verify its application, we had to design a test stand which would house the sensor and also periodically expose it and remove it from the flow. This periodic actuation of the flap in front of the piezoelectric sensor caused disturbances in the flow, and this is necessary as the signal of the piezoelectric sensor actually decays over time, so this periodic disturbance is necessary in order to maintain a constant signal. The test stand included a pedostatic probe to measure the dynamic pressure of the airflow that the sensor was exposed to in order to compare the voltage signals received from the sensor to the dynamic pressure of the flow. A charge amplification circuit was outside the wind tunnel, and the wires from the sensor to the circuit were run through the test stand out of the wind tunnel. In order to create a correlation curve between the voltage received from the output of the amplifying circuit and the dynamic pressure acting on the sensor, we we needed to test the sensor at various speed settings. We set the wind tunnel at these various speed settings and then started the flaps actuation after the speed was achieved by the wind tunnel. The signal was recorded by LabVIEW for the duration of the flap actuations. A majority of the noise was actually due to the vibrations in the wind tunnel and due to the vibrations from the actuation of the flap itself. And due to the decay, you can actually see in figure 4, actuation is required to achieve a steady state peak-to-peak voltage value, as achieved by the end of figure 4. The results from the testing as specified at these different values, ranging from dynamic pressures from 0 to 308 pascals. We created a correlation curve which was highly linear. This highly linear curve is very good, as it actually shows that we have good reliance and we're in a very linear region of response of the materials. It is important to note that the error bars shown are actually the standard deviations of the recorded values. So you can see that there were some high deviations in the values. And it's also important to note that there is a steady state offset. This is due to the vibrations both in the actuation and in the wind tunnel itself. In conclusion, there is a strong correlation between the peak-to-peak voltage of the PVdF sensors and the dynamic pressure ranges tested. That means that these sensors can be used in aerospace applications. There is further work to be done in improving the response and reducing noise. Currently, we are working on redesigning the test stand to further improve the fidelity and reducing the noise in our setup. And from there, what we could do is we can actually redesign the charge amplification circuit based off of variations that can potentially produce more noise canceling effects. We can test PVdF sensors that are created through additive manufacturing, which as shown there, we are working with a team from Purdue, which has currently created said sensors, and we will work with them to test these sensors and actually see if they can be a useful alternative to the commercially available PVdF sensors. And additionally, we can adapt PVdF into a pressure mapping sensor for airfoils, as done in reference 3. This application is really important as it allows for a very useful, potentially lightweight, and potentially cheaper alternative to pressure taps, which can be used without interfering with the airflow directly, and could be used to get active information about the airflow around an aircraft as it is traveling through. This is a very nice application as it allows for the potentially speeding up and making control surfaces for aircraft more useful, as they will now be responding to the cause of several issues instead of the issues themselves. The redesign to the test stand is shown in figure 6. So I would like to thank and acknowledge Dr. Kanistras for this opportunity and his advice throughout the summer, Dr. Nawrocki and Jinsheng from Purdue University for providing us with 3D printed PVdF sensors and their assistance in understanding piezoelectric sensors overall. Eli Merlock from UAH as well for his invaluable assistance with the testing stand and helping with all 3D printing issues. And finally, the RCEU staff, the UAH Office of the Provost, the UAH Office of the Vice President for Research and Economic Development, the Faculty Senate Finance and Resource Committee, and the Alabama Space Grant Consortium for the opportunity to conduct this research under the RCEU. Additionally, I would like to thank the Honors College. Here are my references.